We'll solve this problem using the solving methodology outline we have in class. So the first step we do is a sketch. So we have a block on a horizontal surface. We have somebody pushing it by an applying force, and we have friction, so we just make a little bit of a ripple here. The second step is to do a free body diagram of the object. So we have the box, we have a force of gravity acting on the box, we have a normal force acting on the box, we have a frictional force, and this is the kinetic frictional force, and then we have that pushing force exerted by the person onto the box. Since we're dealing with Newton's second law, it's a vector equation, and we want to find something about some quantitative information, we need to break it into component forms, and for that we need to establish a reference frame. I like to put the reference frame at certain time. That is not required for this problem to just solve for the acceleration. However, we will go to use kinematics if we want to know something about the position. The position relates to an origin at a given time, in the case it becomes important. So if you use a standard Cartesian coordinate system xy like this, and of course we look at the box as being a two-dimensional planar object here, then step 4 is to decompose the vectors into the components according to the reference system. We may recognize that all the vectors are co-aligned with these axes, so it makes it easy, no trigonometry is needed. Okay. So first we can look at our x, and we can see that we have force of friction as an x component. We know the force of friction. Now we can implement the useful tools or equations we have for a variety of forces, like the frictional force. We know that is the coefficient of kinetic friction multiplied by the normal force. And since this is a frictional force in the x direction, this normal force must be the y component. We can also see from our reference frame and the free body diagram that this must be a negative component. For the force of gravity, it has no x component, so that is simply 0. We have our normal force, similar, is also 0. And then we have our pushing force, which is directed in the x direction. And as such, it is simply the magnitude of that force itself. And then it's in positive direction, so we can put a positive on there. We can do the same thing in y. In this case, again, we take our frictional force. There is no y component. Our force of gravity is all in the y direction, but it's in the negative. We use the helpful equation that the force of gravity is mass times the acceleration of gravity. The normal force in the y direction is pointing up in the positive direction, and that's the component of it. So you can say plus Fn. And then finally, the pushing force does not have any applied component in the y direction, so that's 0. All right. So that is, these are all our components. And then we're now ready to do the next step, step 5. And that is simply taking Newton's second law in the two components, x and y, and insert the information we have. So if we make a little, I think I do that right here, a little vertical line, I can say the sum of the forces in x must be equal to mass times the acceleration of the object in the x direction. Now we simply take these and add them together. So we have a positive pushing force, we have a negative contribution from the force of friction. Now we could write subscript y here as well, but we may also recognize from the decomposition of the normal force in the y direction, that is simply just the normal force. So leave it at that, mass times the acceleration in the x direction. Okay. We can do the same thing for the y direction. And now we can start with the normal force, subtract mass times the acceleration of gravity, equals mass times the acceleration in the y direction. So now we have Newton's second law written out in two components. We have all the information we inserted from the helpful equation for the forces. And now we look up, or we count how many unknowns do we have, how many equations do we have. So the pulling force is given in the problem. We know the coefficient of friction is given in the problem. Normal force is not, that's an unknown. The acceleration is what we're looking for. It's also an unknown. Go to the other one, we know the mass, we know the acceleration of gravity, we don't know the acceleration of y. That means we have three unknowns, two equations. This is not in our favor. So we go to step 6. That is the equation of constraint. So in this case, we know that the y-coordinate is going to be 0 all the time. The box is constrained to move on the surface, hence an equation of constraint. So that is equal to 0. So how do we say the y-coordinate of the box is equal to 0? And that also implies that there's no change in the y position of the box, and that simply implies that the acceleration of y must be equal to 0. This is the third equation that will help us then solve for it. So now you can write it down again. So the question is, can we solve it now? Yes, we can. So we can write for our x, we have the pushing force minus the coefficient. The normal force equals mass times the acceleration in x. For the y direction, we now have the normal force minus mass times the acceleration of gravity is equal to 0 by applying the equation of constraint. Now, the pushing force is known, coefficient of friction is known, normal force is not known, acceleration is not known, here's no new variable introduced. So we have two equations, two unknowns. We find our favorite tool to do that. If that's on paper, it's okay, just time consuming. So I will show you how we can do it using symbolic Python.